Hello friends, welcome to lecture series on essential mathematics for machine learning. So, we have seen that what functions are and what are the various properties of functions. When a function is said to be a 1 function, many to one function, on to functions, or what an identity function is, what an exponential function is, etc. we have seen in our last lecture. Now, we will see that when we talk about continuity or differentiability of a function of a single variable function, here we are talking only about single variable function, that then what do you mean by that? When we see that limit of a function exists. So, let us see all those concepts here in this lecture. So, if we talk about limit of a function at a point, so what does it mean? Let f from x to y, where x and y are subset of R, be a function. Okay, we are taking only a one variable function over here. Then limit x tends to a f x equal to L. What does it mean? It means that if and only if you have limit x tends to a plus f x equal to limit x tends to a minus f x equal to L. This basically means right hand limit a plus, this limit is basically the right hand limit, and this limit is basically called left hand limit. So, what does it mean? So, let us try to understand first, and then we will discuss few example based on this. So, if you are saying that limit x tending to a f x, first of all it does not mean that we are putting x equal to a, it is a limit. Limit means we are approaching x towards a. That means, this means that as x tending to a, suppose it is L, this value is suppose L, this means what? As x tending to a, f x is tending to L. Okay. So, graphically what does it mean? Suppose you have this type of function, okay. Suppose this is your x equal to a. Now, if you approach towards this a from the left side, which is a minus, okay, very near to a, no matter how small you are taking from left side of a, and or you are taking towards right side of a, and these two limits are coinciding and equal, okay, that means this limit exists and is equal to L. That what I want to say, that this means that left hand limit, or we can say that we can simply write it like this, that limit x tending to a minus f x is equal to limit x tending to a plus f x, both are equal and equal to L, then we say that the limit exists. Okay. So, say now you take this function, say signum function. Signum function is a very popular function, it is defined like this, f x equal to mod x by x when x is not equal to 0, and it is 0 when x equal to 0. That means, it is equal to, see we know that mod x is x when x is greater than 0, and it is minus x when x is less than 0. So, if it is x when x is greater than 0, this means this value is 1 when x is greater than 0, this is minus 1 when x is less than 0, okay. This is 0 when x equal to 0. So, the graph of the function is something like this, when x is positive it is 1, this function, this is this line, and when x is less than 0 it is minus 1, that is something here, and when x is 0 it is 0. So, it is not included, it is also not included. Now, suppose you want to find out limit when x tending to 0 of f x. So, what is this limit equals to? Now, you can clearly see that when you approach to 0 from the left side of this graph, so it will tends to minus 1 from here, the value of the function will tends to minus 1 from here, and when you approach this value, this function from the right side, then this value will tends to 1 from this side, and minus 1, since minus 1 is not equal to 1, that means this limit does not exist. So, we can say that this 0 plus is what 1 and what is limit extending to 0 minus? 0 minus of f x, it is minus 1. So, since the two limits are not same, so this means limit x tending to 0 f x does not exist. Okay. Now, say you take another example, say you take a box x function, the greatest integer function which we have already defined, it is a greatest integer function less than equal to x. So, how we define it? How we plot it? See, when x is between 0 and 1, it is 0, it is open here. When x is 1, it is 1, and from 1 to 2 it is 1, and from 2 it is open, at 2 to 3 it is 2, and so on. And similarly here at 0 it is 0, okay. So, it is open here, and at minus 1 it is minus 1, and similarly we have a step type function over here like this. Now, suppose you want to calculate limit x tending to say 1 integer point of f x. If you take x equal to 1, this is x equal to 1. Okay. Now, if you take this, if you approach this point toward the left side of this graph, if you take the left side of this graph, this value is from the left side, this value of the function is 0, and from the right side this value is 1, the value of the function is 1. So, since 0 is not equal to 1, this means this limit does not exist. Okay. Or you can show mathematically like this, you will find left hand limit x tending to 0 minus of f x, which is box x, which is equal to limit h tending to 0, you will put x equal to 0 minus h. So, it is 0 minus h where h is tending to 0. Now, when h is tending to 0, that is if you take a h very small tending to 0, then this 0 minus h will tends to, it is we are calculating at 1, not at 0, sorry, it is at 1. So, we are calculating at 1. So, this is 1, this is 1 minus h. So, when we take a point very near to 0, but not equal to 0, and it is 1 minus a small quantity nearing tending to 0, it will give the value less than 1 whose box is 0. So, this is basically gives equal to 0. Now, when you take the limit x tending to 1 plus of box x, that is right hand limit. So, this is limit h tending to 0, this is 1 plus h over here, x is here, x is 1 plus h, and this is basically what 1 bigger than 1, and the bigger than 1, the box will be 1 only. So, this means this 0 is not equal to 1. So, that means this limit does not exist. So, limit of the function basically means what, when we approach toward from the at that point, if we approach from the left side and we approach from the right side, the value should coincide and value should coincide, I mean value should be same, that then we can say that limit exists. And the value are not same or they does not exist, then we say limit does not exist. So, see these are few examples, quickly we can see, this is only for recap of this definition what we have discussed. Suppose you want to find out the limit x tending to 2 of this function. So, how we can see you want to find out limit x tending to 2, suppose x square minus 4 upon x cube minus 8. So, this is equal to what? See, when x is tending to 2, it is when x equal to 2, we do not know that what this function is, but x tending to 2 we want to find it. So, limit x tending to 2 it is simply you can factorize it. So, a factorization it will give this value, this 2x plus 4. Okay. Then when x is tend to 0, these fractions can be cancelled out because they are not equal to 0. So, now you can substitute x equal to directly because this is defined at x equal to 2 now. So, it is 4 upon 4 plus 4 plus 4, that is 1 by 3. So, this is how you can find out this limit. Similarly, if you want to find out the second limit, so second limit is what? Limit x tending to 0, it is 1 minus cos 1 minus cos x. So, it is 0 upon 0 form. So, what you will do? You will simply find limit x tending to 0, 1 minus 2 sin square x from the formula of cos 2 x. It is 1 minus 2 sin square x by 2. So, this is what? This is limit x tending to 0, 2 sin square x upon 2 sin square x by 2, 2 cancels out. So, it is limit x tending to 0 sin, we can write it like this, sin x square sin x by x whole square upon sin x by 2 upon x by 2 whole square. X square will cancel out, and it is what? It is 1 into 1 by 4. Yes, we can write it like this. And as limit x tends to 0, sin x upon x will tends to 1. Okay, this we can easily show. So, this is equal to 4 now. So, this limit is equal to 4. So, similarly you can factorize this and you can find out this limit, and for this we have already seen that this limit does not exist. Here this box, this is a greatest integer function, we have already seen this. So, this is how we can discuss about limits. If you want to show the existence of these, you can find out, of course, you can find out left hand limit and right hand limit, and you can show that that they are equal to say that this limit exists. Okay. However, we can quickly see that such functions, for such functions, limit exists at a given point. Now, if we talk about continuity of a function at a point, what do you mean by that? Now, continuity simply means at a point that limit of a function at a point should be equal to the value of the function at that point. And what do you mean by this existence of limit? This means left hand limit and right hand limit must be equal, and instead of L we are having f of a, that is the value of the function at that point. So, if these three things, if limit exists and it is equal to the value of the function at that point, then we see the function is continuous at that point. So, let us try to understand this concept also graphically. Continuity of a function at a point, say x equal to a. Say you have this type of function, any function you are having. Okay. Now, say it is x equal to a. If you approach toward this a from the left side or from the left right side and is equal to the value of the function at this point, which is f a, if all these points coincide, then we say the function is continuous at that point, there is no break in the function. Okay. Now, suppose you have this function, say you have this function, any function, this is x equal to a suppose, and at x equal to a the value of the function is here, suppose. Here you are having a hole, I mean this is not defined over here, at x equal to a value of the function is here. Okay. Less than a the function is defined like this, and the greater than a it is defined like this, but at x equal to a the value of the function is here. Okay. Now, when we take the left hand limit, it will exist and equal to whatever function expression of function you are having, you can calculate from that expression. From the right hand limit also exists, and that also you can find out. So, we in this case the limit of the function exists as seen from the graph, but since it is not equal to the value of the function at that point, so we see that the function is not continuous at this point. Okay. Because left hand limit will give the point somewhere here and the right hand limit will give a point somewhere here on the graph, but it is not equal to the value of the function at that point. So, that means this function is not continuous at x equal to a. Okay. Take another example, say okay, this function we have already discussed, which is signum function. This is also of course, if for this function since this function is not even limit exists at x equal to 0. So, we cannot talk about continuity, since when limit does not exist, this means function is not continuous at that point. Okay. So, in the same way we can construct various examples where function is continuous or where a function is not continuous. Okay. Now, suppose you have this problem and you want to see that this function is continuous at a function break at x equal to 1. When x is less than equal greater than equal to 0, it is defined everywhere, which is given by 1 plus x. At x equal to 1, it is 2, and when x is between 1 and 2, it is 2x. Very simple functions I have taken, and we want to see we want to show that the function is continuous at x equal to 1. So, how we can prove it? So, what is f x here? F x is 1 plus x when x is between 0 and 1. Okay. Okay, it is also 2, fine. So, the value at x equal to 1 comes from here itself. So, we do not need this expression in fact. It is 2 when x equal to 1, and when x is greater than equal to 1 less than equal to 2, it is what? It is 2x. Okay. So, if you want to show that function is continuous at x equal to 1, we have to find out left hand limit first of all at limit x tend to 1 minus of f x. Now, when x is less than 1, f x is what? 1 plus x, okay, and it is limit h tend to 0, we can replace x by 1 minus h. So, this is clearly 2. Now, when you talk about right hand limit, which is limit x tend to 1 plus of f x, it is equal to limit x tend to 1 plus, means more than 1, more than 1 it is 2x. So, which is equal to limit h tend to 0, you replace x by 1 plus h, which is again equal to 2, and what is the value of the function at x equal to 1? It is 2. So, since all the 3 things are equal and equal to 2, that means function is continuous at x equal to 1. Now, what are different properties of continuous functions? If you are having 2 real valued functions, suppose they are continuous at x equal to a and alpha be any real number, then the sum and difference of 2 continuous function at a point is also continuous at that point, same point. Alpha times f is continuous at x equal to a. You see, it is given to you that f is continuous at a point x equal to a. The product of the 2 functions f into g, this is a simple product of 2 functions, is also continuous at x equal to a, and the division of 2 function f upon g type is also continuous at x equal to a, provided g a is not equal to 0. So, these are few properties of continuous functions. Now, what do you mean by differentiability of a function at a point of single valued functions? So, if let f be a real valued function defined on an open interval a b, and let c is a point in between a to b, then f is said to be differentiable at a point x equal to c if and only if this limit x into c f x minus f c upon x minus c exist. So, if this limit exists, we say the function is differentiable at a point x equal to c, okay, and we denote this by f dash c or d by dx of f x. Now, what do you mean by the existence of this limit? This mathematically this means that left hand limit and right hand limit exist, and you replace x by c minus h here for the left hand limit. Less than c means c minus h, greater than c means c plus h. So, you replace x by c minus h here, you will get this expression where h tend to 0, and you replace x by c plus h over here, you will get this expression. So, if these two expressions are equal, then we say that function is differentiable at a point x equal to c here. And geometrically, what does it mean? Geometrically, it means that if we say that a function is differentiable at a point, geometrically it means that there will exist a unique tangent at that point of the function f. Okay. So, if we talk about differentiability, say you have this type of function. If we talk about differentiability of function at this point, say this is p, then this means there exists a tangent at this point, unique tangent. If we talk about differentiability at this point, this means there exists a unique tangent at this point, unique tangent at this point. This function is through differentiable. Okay. So, differentiability at a point f dash c, which is also like d f by dx dot x equal to c, also we can write like this. This means what? This means limit x tending to c f x minus f c upon x minus c exist. And existence means, of course, we have already discussed, existence means that left hand limit is equal to right hand limit. Okay. So, suppose these are few examples, suppose you want to show that this function is differentiable at x equal to 1. So, first of all, if you are talking about differentiability at a point, then this means that function must be continuous at that point, otherwise we cannot talk about differentiability. Okay. And if a function is continuous at a point, this clearly means that the limit of the function exists at that point. But if a function is continuous at a point, then the function may not be differentiable at that point. Say for example, we have mod x, see we can discuss that. Say you have function from R to R, which is f x equal to say mod x, modulus function. So, how we can plot it? We can plot it like this. Now, if you talk about continuity of this function at this point, say x equal to 0, at x equal to 0. So, when we approach to the left side or you approach from the right side, very small to x equal to 0, it will tends to 0. But when we talk about differentiability of this function, from the left side, differentiability means slope or tangent at that point, and it must be unique. When we talk about a tangent, slope or tangent of this function from the left side, it is minus 1. You can see this is minus 1, and if you see take the slope of this function from the right side, it is plus 1. So, that means the function is not differentiable at x equal to 0. However, it is continuous at x equal to 0. We can also show it. I am not discussing the proof here, but you can also prove it by using the definition of continuity or differentiability. So, if at a point from the left hand side you will get another slope and from the right hand side you will get a different slope, then we say the function is not differentiable at that point. Okay. So, now let us discuss this example, very simple example, and we have to show that this is differentiable at x equal to 1. So, f x is what? F x is 2x when x is less than equal to 1, and it is x square when x is greater than 1. Yes. So, we can find this, we have to find this limit. Yes, at x equal to 1 we have to check at x equal to 1. So, that means we have to see the existence of this limit at x equal to 1. And that means we have to see that whether left hand limit or right hand limit exists or not. So, first we will see left hand limit, that means limit x tending to 1 minus of f x minus f 1 upon x minus 1, and then we can also see about right hand limit. So, this is basically equal to limit h into 0, this is you replace x by 1 minus h, okay, minus f 1 upon minus h, and this is what? This is equal to limit h into 0, you replace x by 1 plus h over here minus f 1 upon h. This is further equal to what? Limit h into 0, f is, see 1 minus h means this is less than 1, and when less than 1 means 2x. So, it is 2 times 1 minus x. So, replace x by 1 minus h, okay, and f 1 is 2 upon minus h. So, let us compute this first of all, 2 cancels out, minus h cancel out, it is 2. What is the value here? So, it is equal to limit h into 0, 1 plus h means now it is more than 1, more than 1 means x square, then it is 1 plus h whole square minus 1 upon h. So, it is limit h into 0, it is 1 plus h square plus 2 h minus 1 upon h, and 1 cancels out, and this is also equal to 2. So, these two values are equal, this means this limit exists and equal to 2. So, that means this function is differentiable at x equal to 2, and what is f dash 1? F dash 1 is 2. So, these are some illustrations. See, I want to give a picture that how you can visualize that whether a function is differentiable, continuous or not at a given point. Okay. Because then we can talk about partial derivatives or other concepts of calculus. Okay. So, in this way if you want to find out check whether a given function is differentiable or continuous, we can use this theory and we can analyze the shape or graph of the function. Okay. So, this is also this second example we can also investigate using the same theory whether this is differentiable or not. Here it is not differentiable at x equal to 1, we can easily prove it using the concept which we have discussed in question 1. These are simple some rules of differentiability for single variable function. If alpha times f is same as alpha times d by dx of f x, sum of difference of two function, I mean d by dx of sum and difference of two functions equal to d by dx of first function plus minus d by dx of second function. D by dx of f into g is equal to first function derivative second function plus second function derivative first function, this is product rule. And the quotient rule is what? Denominator derivative numerator minus numerator derivative denominator upon denominator whole square, and this is of course denominator should not equal to 0 for any x, provided these rules valid, provided both are differentiable functions. So, these we have already studied in our 11th-12th classes. Okay. This is simply a recap of those things which we have already done, and these theory we will use in our forthcoming lectures based on the calculus. So, thank you very much.